Dangerous Woman by Ariana Grande, because we're talking about some real dangerous shit today, okay? Which is imperative programming. So, all right. Today we'll be talking about imperative programming, which I know you all signed up to take and sign up to be in this class for. But I think this one's kind of an interesting class because people are like, oh, imperative programming, like you're betraying your course. But here's the thing, we're not, because they actually named their course after our mascot. You see, imperative programming. So think on that for a second. All right, we're a superset. Anyways, one other thing. Let's see. So. Is that me? Okay. All right. Okay, cool. Just making sure. Right. Okay. This is the first of the lectures before the special topics lectures and the final lecture. But today is definitely still fair game, and I definitely think that next week's lectures are going to be even cooler. Compilers and program analysis are my specialties, and I'm really excited to kind of talk to you about them. If you've heard me harp on about the compiler, hopefully next week I will make some of those things clear to you, what I was talking about, okay? And program analysis is another cool thing. And then I am going to send out a Piazza post about this soon, but I'm requiring everyone come to the final lecture. Okay, let's get on with it because I'm already 3 minutes behind. So we're talking about imperative programming today, which is kind of interesting, but also kind of not. We'll talk about this idea of mutability that I alleged to in the first lecture. We'll talk about reference cells, which are a particular kind of type that we can use a kind of data structure for mutability. We'll look at some uses for refs, look at an example, and then I'll tell you some special applications of mutability that I use as someone who works in a functional language, some little tips and tricks I do as a result of this thing. Okay, but let's get into it. Okay, so first off, mutability. All right, oopsie. That's not right. All right, I'm gonna have to do this thing again where I go here and then I go all the way to the top and then I delete this handy little annotation here that says handout because it means that my presentation was not compiled with pauses in it. But mutability is the thing that exists. And I've kind of harped on at you all the time about how it's really a bad thing. And I stand by that. We want to make sure we don't have unsafe behavior. And mutability kind of, if you remember what I said during the first lecture, means that if you ever do anything, you have to be aware of everything that's happened in the entire program's history, which is no bueno as far as software engineering goes, or as far as writing programs goes, because it's going to make things just really hard to reason about. Okay, boom. So the idea is just that we want to avoid footguns that will make us write incorrect code and write unsafe code. And mutability is one of those footguns, right? So let's try to avoid that. But we've been doing that up until this whole point. We've been working with purely pure code, which is code that always returns the same output given the same inputs because we got predictable behavior. But we've been talking about purely functional stuff for the whole semester. Well, we've been lying to you because mutable features do exist in standard ML. And that's what we'll be talking about today. And this kind of makes sense because it's really hard actually to get away from effects as a whole. For instance, like in an earlier lecture, we saw with exceptions, we can now have addition, where addition is now no longer commutative. Does everyone remember that example? If I have raise div plus raise bind, right? If I invert the order of these arguments, if I swap raise bind for raise div, raise bind will happen first, which means bind will be raised. But in this permutation, div is raised first. Two different exceptions, different extensional behavior. So addition, in the presence of exceptions, is not commutative. So we've already seen the effects can kind of ruin our day when it comes to our code. So we haven't even gotten away from it purely. Or for instance, in this function here, foo, I have val x binding this loop function, which I never defined for you, but you can assume is the looping computation, and then y, which raises div. Now, is it safe for me to permute these? Can I switch the order of this? What do you think? Yes or no? No. Why? What'll happen? If x loops forever, y raises div. If I put one versus before the other, I get different behavior. But that shouldn't be the case. I should be able to be like, these are independent. I don't need to think about it. I don't care. Let me just do it in whatever order. But not the case when it comes to things that loop forever and things that raise exceptions. So we already lose some of these nice properties. And extensional equivalence becomes weird to reason about when you're kind of in the presence of the outside world. What I mean by that is, I've tried steadfastly to avoid talking about this. Maybe you've come across it, but there is indeed a print function in standard ML. It's not very convenient to use, but it has this type signature. And printing is kind of cool because what it does is it's a normal function. I give print a string and it returns to me a unit. And then all it does is it prints out to my terminal, to my console, right? But this is kind of interesting because what it does is that when print gets a string, it always returns to me a unit, right? This guy. And that means that for any choice of S, I should have that unit is extensionally equivalent to print of S, yeah? Because this is going to evaluate to that. Except, like, what do I mean by extensional equivalence? Because remember, one of the big features of extensional equivalence I talked about in like the first week is I should be able to swap equals for equals. If I have two EEQ things, I should be able to replace one with the other wherever I see it. Now, if I replace every unit everywhere in my program with print of high, do you think my program is going to display exactly the same behavior observationally? Indeed, it will not. Okay, I don't need your sass. It will not, because I'm going to get a metric buttload of prints of high everywhere when I should have gotten unit. Okay, so printing also kind of makes this idea wrong. So mutability just makes us have to reconsider our lives and reconsider our definition of extensional equivalence. All right, so we're kind of working from behind here. All right. So life is cruel. We live in the physical world. All right. I give you two reasons why effects ruin our day. Here's number three. We live in the physical world. We can't get away from that. I try not to live in the physical world as much as I can, but unfortunately, our computers are made of silicon. So at some point, we have to be able to interface with the real world. We have Unix. We have POSIX libraries. We have a bunch of like machine code running beneath everything. So we have to think about that sometimes. All right. So what I'm trying to get at here is like, what can we do to make sure that we still have safe code, but we have the ability to do this kind of stuff when we need? How can we avoid book guns, but still be able to dip a toe in, okay, make it a toe gun if we so wish? So the idea here is just that we want to avoid book guns. We don't necessarily need to prohibit them entirely. Our approach up until today has been that we want to prohibit book guns. We have no mutability anywhere. You know, I try steadfastly not to tell you that print exists. I try to tell you that what I'm telling you about today doesn't exist. But all we need to do is be wary and cognizant, because as long as we do our best not to dip the toe in, we'll be fine. All that matters is that we have that caution. We don't do it by default. Okay? So another way to put this is like immutability and purity. These are concepts that we invented for our purposes, but we don't serve them. Like they're not in charge of us. I can have a relatively immutable and pure code, but I don't need to bend over backwards to try and make it happen. Some languages will try to make that happen, but in SML, we're gonna say it's okay sometimes to be a little mutable, as long as it's a little bit. Okay. But to make sure that we don't have mutable code all over the place, like with C or anything, we make it opt-in. And this is a big idea in programming languages, okay? We want mutability to be opt-in. If I'm writing C code, okay, and I don't, forgive me if you don't know C, but like the syntax would look something like this, right? I could say int x equals 2, and then any point down here in the program, I might say x equals 3. And this is an assignment. It's saying, hey, this x thing that you depended on, it is now 3. It now contains 3. That's mutable. And every single assignment ever in C exhibits this behavior. It might mutate something. I don't know for sure. That's the opposite of opt-in. That's by default. Mutability by default. What we're going to do is take this track where if you want to use mutable features, you've got to work for it. You've got to tell me explicitly, I want this to be mutable. If you've worked in other languages like, I think JavaScript has this now, and Rust, they also have this kind of idea, sort of. Okay. And in a different context, sort of, you know, this thing about null pointers, which is I can have a pointer to some memory location, and it can be this thing called null, which is really 0, and that means no bueno. It means don't go there. It means giant, you know, yellow fence, because if you try to go to null, you're going to crash your program. Okay. This is commonly known as Tony Hoare's $1 billion mistake. His words, not mine, because he actually said this, and it's pretty accurate. Okay. So the way that we solved this problem in SML, right, is instead of having everything be null by default, instead of having everything be possibly null, what did we invent? We invented this idea of sum and none, sum of v and none. But this showed up in the type. This was of type T option. we had a specific type that we invented for the purpose of if we wanted to dip a toe into possibly not having a value, but not on by default. So that's the thing I'm trying to show you here with what we're doing. Okay. All right. I need to hear some. Okay. So you all are the future of computer science. So I need to hear you say something for my peace of mind. Everyone raise your hands. Okay. Everyone raise your hands. I need to hear you say, repeat after me. If I invent a programming language, I will not put null pointers in that programming language. That was wrong. That was wrong. Don't listen to him. Okay, now I can sleep a little bit better at night. Thank you. All right. That was for my benefit, not yours. All right. So let's take a similar approach with mutability. Context switch, reset. Next slide. Ref cells are going to be our solution for this problem. What we're going to do is introduce, we're going to introduce, just like how T option is the type of optional values of type T, that is, we may or may not have a value of type T. We're going to have a new type that indicates mutable storage, storing a value of type T. And that type is going to be tref. Okay. So in fact, you can say that alpha ref is a type. And this has concrete instances as intref and string ref and so on and so forth, right? And the idea behind a type of tref is that it is a box that contains a value of type T. All right. So when you ask me what is a tref, that's what it is. It is a box that contains something of type V. But beware, because I'm lying to you right now, because I said the box contains that. I mean the box contains that at this point in time, because somebody might come in and sneakily erase it and then put 2 in it or something. I don't know. Okay, so everything I'm telling you is very transient. I can tell you something about refs, but I can only tell it to you for now, okay? Because it might change on you. So the type of boxes is what I want to get across to you, okay? And the box is allowed to change what's inside, but the box stays, all right? The box stays the same, but the thing inside the box might change, okay? That's the idea. For anyone who knows imperative programming, I'm telling you that this is a pointer to some kind of like mutable state, right? But the difference here is that we're making it fully opt-in, as in, there's a type level distinction between immutability and mutability. If I have something of type int, I know this is immutable. I know this will never change on me, but only if I explicitly am holding, and I'll show you how we create this value in a second. If I'm explicitly holding something of type int ref, I'm saying, okay, I know this will change on me possibly at some point in the future. It's like I'm signing the EULA. Okay, I'm waving away my rights to have safe code when I see this. Okay, like that's on you, right? I'm signing this agreement, but I don't opt in. Okay, or I don't opt in by default. I have to explicitly opt in, and we can make it very easy to see where these things can go wrong now. Okay, so types guide structure. Who would have guessed? Okay, and that's the idea behind refs. So there are a few primitives that are going to be useful for doing this. There are a few primitives that are going to be useful for doing this ref thing, and they are as follows. The first one is actually a constructor called ref, takes in a value of some type alpha, and remember that polymorphism means this doesn't need to be alpha, it could be int or string or whatever, and then it promotes it to a value of type alpha ref. Okay, that is, it puts the value that it gets in a box. I also have this one, which is pronounced bang, the bang operator. And bang has the type that it has the inverse. If you give me a ref, it's going to take whatever is inside that ref. It's going to dereference it, to use a certain terminology. Okay. And then finally, this one is contentious. It's colon equals. Okay. You can pronounce it walrus. You can pronounce it assignment. You can pronounce it colon equals. I usually say colon equals. I think my TAs are a fan of walrus. But this thing is how I change what's inside of a box. So I say that I take in an alpha ref. Oh, this is an infix operator, by the way. Let me write that. It's infix. And it takes in the alpha ref star an alpha value. And what it's going to do is it's going to change whatever's inside this box to be whatever I gave it. But the thing is that once it does that, it doesn't really do anything interesting. It just does that as a side effect. So what I'm going to do is I'm going to have it return this. It returns a unit, as in it returns nothing interesting to me, because there's nothing that it computes. It doesn't compute to me a meaningful value, but it executes a side effect. So whenever you see a function that returns unit, you should immediately think side effects are going on. Okay. Like maybe it's a printing function, or maybe it's, yeah. Not a pure function. I would say so, because if you give it the same functional value, you might get different results out. Yes. So it is not a, yeah, not a pure function. Okay. Boom. That's exactly what I just said. All right. And this will be for creation, modification, creation, access, and modification of ref boxes or reference cells. Okay. And I will go deep into what each of these do. All right. If everyone's cool with that setup, we'll move on. Okay. So what does ref do? Well, I told you that ref just takes in something and puts it into a box, right? And I guess I can just show you this. So I have ref of v. If I have ref, actually, let me be more specific. Right? I usually don't think I need to stress this point to you, but you know, if I have ref of e, where e is not a value, right? Ref is just a function. Okay, so this has no special behavior. So what happens first? What happens if I have ref of v, or ref is a function? What's the first thing? You all know this. E steps to v, or e, you know, evaluates to v, hopefully. All right. And then if that happens, then what happens is box happens. All right. We get a box. And one thing to note is that the value that we get here, like this value here, this, you know, let's say it's an int ref, okay? The value of this int ref is the box. It's not the contents of the box, it's the box. I'm binding a variable to the box when I say something like, you know, val x equals ref of e, okay? The box is ultimately what I'm holding, what that variable is associated to. And it's also worth noting, and this will be important for you to cognize on your homework, every time I call ref, I get a new reference cell, okay? A unique reference cell. Different calls to ref give me two completely unrelated reference cells. Think not of memory addresses and like positions in the system. They just exist. They float in the ether, okay? That's all that matters, all right? But every time I call ref, I get a reference cell. Now, I have to stress this to you because this is a mistake students make every semester. But on your homework, if you call ref too often, you will mess up. If you call ref too little, you will mess up, okay? You need the Goldilocks ref, okay? Call it the right amount. But understanding this will help you, okay? One ref, one box, okay? And read this thing I was talking about, which was the null pointer thing. This actually is still fine because a ref box can never be empty. Because in my constructor, well, I put it away, but in my constructor, which is ref, I can never not have my alpha value. So I must put something in the box, and I have to have something to replace it with if I change what's inside. So my box can never be empty. So there's no such thing as a null pointer still, unless I put like an option in there very intentionally, right? But I can't get like a segfault still. I can't get like an unsafe memory access. Yeah. Yeah, let me give you a very concrete example. So if I did something like this, I said val, and I have some pretty diagrams for later, but I said val r is equal to ref of 1. The contents of the box I want to put in are the arguments to ref, so it's 1. So what this will happen is that r is now bound to a box. So this box is r, because it's the ref, where the box contains 1. Does that make sense? Yeah, okay. Yeah, I have plenty more examples to show you. But yeah, good question. Cool. Okay, any other questions on that? Yeah. Okay, sounds good. Sounds good. You know, in terms of like your tuition costs, like that probably cost you like dollars of just that second that you lost. And actually, I'm losing more by me speaking about you losing. Yeah, okay. Let's move on. So ref creation once per call to ref. That's what I want you to know, okay? No sharing, no nothing, all right? And so let's look at this code here. Oh yeah, I say R1 is equal to ref of 1. R2 is ref of string 5, and R3 is ref of 0. Okay, and I think I'm going to actually not draw this for you because I have very pretty pictures for you. Okay, so one ref, one box. Over here on the right, I have something I call the store. It's kind of like I think it's a programming language theory kind of term, but the store basically meaning where we keep all of our mutable data. Okay, so right now it's empty. Assume that this is the beginning of the program, but let's go to the first line. So if I try to evaluate ref of 1, boom, I get a box. And this box is what's bound to ref of, to R1, and it contains 1. Then I call it again, new box. The box contains the string of 5. And then I call ref of 0, boom, new box. But now contains 0. All right, this should be fairly straightforward, right? I'm binding each of these boxes to R1 through R3. And that's fine, but I just wanted to illustrate to you how these boxes sort of evolve over time. But what happens next is, what if I want to change what's in the box, right? if I didn't change what was in the box, there would be no difference between this and actually immutable things, right? So I'll use my walrus operator right here. And suppose I did this, which is I say v1 is colon equal to 1, and the v2 is colon equal to string of 1, all right? And if we go back to our picture that we had a second ago, which was this one, right? This is what I got from the previous one. I'm going to execute each line in tandem or in order. So the first one, I say v1 is now 2. All right, so I update what's in the box. And now if I were to do a bang on R1, I would get 2 as opposed to before. Here, I would have gotten 1, right? Yeah. Yeah, it should be. Thank you. R1, yeah. R1, but this now it goes to 2 when I say colon equals 2. And then for R2, if I colon equals string 1, boom, now string 1's in there too, right? Pretty straightforward, I think, okay? We're just changing what's inside of the box. Okay. So seems like we should be able to do anything once we have boxes. We just like put stuff in the boxes, right? Well, there's a lot of subtle things I'm glossing over with respect to how this is implemented. But one such thing is actually, if we had this line here, so I say R2 colon equals 1. Well, first of all, more fundamentally, we would have gotten a type error, right? Which is that R1, if you remember, this thing is going to be of type string ref, right? So ref containing a string. And I give colon equals a string ref and an int. Well, can you find me a substitution of alpha for which that works? Indeed, you cannot. Okay, string and int are just different. All right, so this will not type check. But another fundamental reason for this is just the fact that when you have a box, like we are only capable of storing values of a certain type. Okay, so this restriction actually helps us in that respect. All right, has to do with like compilation stuff. But yes, so we can only store values of a certain type. So let's not think of it as a complete Wild West. All right, we only have control up to a certain granularity. All right. Okay. All right, so I showed you walrus, I showed you ref. Let's talk about how we can take things out of the box. That's going to be our bang operator. I don't really need to say much about this, but if I have bang of R1 and R1 is this ref containing 2, then boom, I put them together and I get 2. All right, but you know, caution, because bang is definitely very impure, right? Because we can get whatever out from dereferencing the same ref. It depends on where we're at in the current state of the program. It depends on everything that's happened up until this point. All right, so be wary of this because the contents of this box lie to you. It won't be the same necessarily. Okay. And then I should also tell you that we can do this via pattern matching. So let me make this let me keep this, but let me try to make this explicit. So in general, it's nice to have these keywords, or not keywords, but these special functions I just showed you that are behind this board. Because it means that when you're using refs, it's very explicit, right? If I want to know where mutability happens, Control F, ref, right? Fair enough. But something else that can happen here is you can also look for bangs. I'll also say this, okay? If I have val R1 equals ref 2, val R2 equals ref string 1, which is what we had earlier. Not exactly the declaration, but this was the state of our store. I can both do bang of R1 at some point and also bang of R2 at some point. But I could also case, and ref is actually going to be a constructor. That means I can case the tuple of R1 comma R2 of, right? And I'm taking a tuple pattern. So my first thing is going to be a tuple. And actually what I'm going to put in is this. Ref of whatever value I expect to see inside, of whatever value I want to pattern match against. So in this case, it'd be 2. And then ref of string 1 goes to true. And if it's not that, let's say it goes to false. Okay. And what I'm going to tell you is that this code right here that I have written on the board verbatim, this will always go to the true case because I'm implicitly dereferencing R1 and R2 via pattern matching. Okay, that's all that's happening. But it's worth noting that there are 2 ways to access what's inside of a ref. We can pattern match or we can do the bang operator. Okay. So equivalently, we could have cased on bang of R1 comma bang of R2 and then remove these refs, if you can see that. Okay. But just something worth noting. All right, cool. So ref is a constructor. Okay, let's see. So we've been using val bindings thus far this semester, which let us sort of do things, or rather, we've been using val bindings in general throughout this lecture to kind of do the side effecty things that we want to. And what I mean by that is like, if I needed to write an expression where I executed some kind of side effect, I would write this, right? I would say let val unit really equals r colon equals 150, let's say. Okay. So this is me saying, let me assign it, and then let me like bind the resulting unit value. I don't really care about it. And then I do something, let's say some expression e. And this just represents, oh, I wanted to return e, but I also wanted to do some side effecty thing. Now this is gross, okay? This is pretty disgusting. So what we're going to do is we're going to have a different way to write this, okay? I shouldn't have to spawn a let, an in, and an end just because I want to do something side effectful. And the syntax for this is going to look like this. And this is a new syntax, actually. E1 semicolon E2, all in parens. What this means is the semantics of this are as follows, okay? 1, I do E1 reduced to V1. 2, I do E2 reduced to V2. So I go from left to right. And then 3, I evaluate to V2. Okay, so I'm saying do the stuff on the left, but also what I really want is this. All right, so instead of this, we could write r colon equals 150, semicolon, and then whatever this e thing is. I'm not going to bother to come up with an example for you. Okay, much more terse, much nicer. All right. And one thing worth noting is actually I can iterate this process. I don't need to do strictly 2 semicolons or 2 things in the semicolon chain. So I could do like r colon equals 0, r colon equals 1. Oh, what? Wait, no, I like the example. R colon equals 1, R colon equals 5, semicolon, R colon equals 0, who would have guessed? And then I do bang of R, okay? So this, I realize it's a little hard to see, but this represents like 3 things I'm doing. I do that assignment, I do that, and I do bang of R. But I fully resolve to this value, whatever it is, yeah. You mean like, does this happen prior to these? Yes, yes. These all happen in sequence before we get to this stage. Yes, sure. Yeah. Yeah, it should have exactly the same semantics as if you did it with a let, actually. Yeah. Cool. Okay, good question. Okay. And the reason why I'm not giving a high choose today is I am out. I need to go to Jiggly. Okay. All right. So we can do this, and this is just a nicer syntax for doing this sequential operation stuff. This is the sequencing operator, all right? And I just told you about that, so we don't need to look at this, okay? Cool. All right, well, that's unfortunate. Quiz time. Let me think for a second to remember what the password was. Oh, I remember what the password was. Let's go. No, wait. I want to put, okay, just get in your positions, and I'm going to write it on the board. Thumbs behind you? Yeah, okay. All right, let's talk about how we can use some refs, all right? There are uses, all right? The ones I'm going to show you right now are pretty convoluted, okay? Okay, so we have 3 fundamental operations for working with refs. So now we can actually use refs to program things, okay? And one of the classic ways we do this is we ask you to implement a function you've seen before, but now we're going to do it with refs. Disclaimer, there's no reason for you to ever do this in your life. You should never introduce mutability for the sake of it, okay? Only do it if it actually has a purpose. And this does not have a purpose. So let's talk about this function, all right? Let's run it through, okay? Maybe I should have written this with you, but the point is, I have my store, which is an int ref, and I store 1 in it, okay? And then at my base case for fact, at 0, I return what's in the store. So I would return 1 here. And then in the recursive case, I say update my store to be n times whatever is in the store. And then I recurse, right? So if you think about this, if I called fact of like 2, I would first multiply what's in the store by 2, then I'd recurse, I'd multiply what's in the store by 1, blah, 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 right? Yeah, actually. And this is pretty cool. So this is this is the fact with refs. Everyone cool with that? Yeah. Yes, they do. Don't say what you're going to say next. So point is, as is typical with any kind of imperative programming, I've lied to you because I very easily made a mistake, and this is just straight up wrong. Okay, and I'm going to show you why this is straight up wrong. So, entirely unpredictable. We write imperative code, and there's a bug. Who would have guessed? But here we are, right? So here's what's happening. What happens when I call fact of 2? Well, let's see. All right, I'm gonna step this through with you, and I have a really nice graphic that I'm not going to use because I hate myself, I guess. But we're gonna draw this out. So I've got my store, and my store at the very beginning, I'm at here. I'm gonna make a box and put 1 in it. Cool. And then I'm going to call fact of 2. Okay, that's where we're at right now. The first thing that happened, right, is I enter my recursive case, and then I say update the store to be 2 times whatever's in the store. So I take this and I multiply by 2, yeah? And then I recurse, so I'm at fact of 1. And now I'm here again, so I multiply what's in the store by 1, so I get 2 again. And then I recurse and I go to fact of 0. And then at the fact of 0 time, I just say, okay, let me return whatever's in the store. So this goes to 2. Okay? What is factorial of 2 2? Yeah, so what's the problem? Well, okay. You're right. Sorry, my bad. I lapsed in judgment. My bad. Let me ask you again. What is fact of 2? Let's do it again. Hold on. Sorry, my bad. Fact of 2, I go to my recursive case and I multiply whatever's in the store by 2. So I get 4. And then I recurse and I go here and what happens next is nothing. Okay, what happens next is nothing. I multiply by 1 and then eventually I return what's in the box. So I get 4. Fact of 2 is 4, right, guys? Yeah, okay, cool. Okay, class is over. Geez. No, it is not, in fact. It's a really bad soundbite. No, it's not 4. And in fact, what was our issue here? What did I say to you? If you make too many refs, you're going to get it wrong. If you make too little refs, you're going to get it wrong. We are straight up in the Papa Bear case. This is, oh wait, no, we're not in the Papa Bear case. We are in the Mama Bear case. This is not enough. This is too little ref. We're using the same ref for the same thing over and over again. Now, that's not necessarily bad, but we're doing the wrong thing here. Okay, yeah. Why don't I just put in a let declaration? Excellent idea. So let's actually try that. Let's actually try that. I don't even have that written out. Let's try that. So I've already illustrated to you why this is bad, but let's try it a different way, right? Let's put it inside. Let's do fact n equals let val store equals ref 1 in case n of 0 goes to what's in the store, or else we're going to update the store to be equal to n times what's in the store, and then return fact of n minus 1. Let's put it in the function. No, it's like this should have been in my slides in the first place, actually. So we got the Mama Bear case. This is the Papa Bear case. All right. Why is this wrong? Why is this wrong? Other than the fact that I'm very gleeful about it. Yeah. Each call to fact makes a new store. We make a brand new ref for every single, not just call to fact, every inner call to fact also makes a new ref. What the heck is going on here? Well, it means that we're going to make, basically, if I call fact of 2, I'm going to immediately have a box with 1 in it. And then that calls fact of 1, which then is like, oh, cool, boss, you told me to make a store. Let me do it. And then I make a box of 1 again. And I never update this at the end of the day. Yeah.
What if you use a wrapper?
A wrapper. A wrapper, exactly. We could exactly do that, like chance. We could make a wrapper indeed. That will be the right way to do it. So what we're going to do is, instead of this nonsense, actually, let me see if I can do a slick move on you. Fun fact prime of n equals, yeah, that actually works. In fact prime n end. Okay, sorry, I know this is hard to read, but the point is that this guy is a separate thing. Thank you. Okay, so this is going to be the correct implementation, because why? When I call fact, I make a singular ref cell. I allocate my ref cell that has 1 in it. Then my recursive function fact prime actually goes and does the recursing. And notably, when I call fact prime doesn't allocate another store. Basically, this is exactly the same thing as that, right? This is exactly the same thing as that. It's just that I put it inside of a function such that every time I call fact, I do this, instead of every call to fact being subservient to the same ref. Yeah. Refs? Give me like 15 minutes. Yeah. Cool. Okay, so if you want to look at my very hard drawn drawings I never used, I'm really sad about. Boom, we go here, and then oh my god, it's updated, and then we go there, and then oh my god, it's updated, and then oh my god, we get 4. Okay, that was the TLDR. All right. Bad things happened, but we know how to solve it, which is this guy. Okay. Notably, this would actually be fine to do if right before you returned bang of store, or well, what you do is you would bind the result of bang of store, and then you'd reset the store to 1, and then you'd return that. That would actually be fine. I'm going to say that'd be a bad style thing to do, though. Like, if you're going to allocate, like, are you afraid of allocating a singular ref cell every call to fact? Like, the ref doesn't need to exist for every single call, right? Unless you're doing some hardcore performance optimizing, okay? Like, fact is a pretty trivial case. So it's possible for this to be correct, but this is not, okay? Try to do this instead. Make your refs local to your function, all right? To the first indication of your function. Okay, and I told you about all of this stuff, and that's the correct one. So let's go. All right, cool. And actually, we're going to get back to something that was mentioned in the very first lecture, and it was mentioned by I'm gonna have to bleep your name, by Arnav. I remember. I'm gonna have to bleep your name out because I want to post these videos, but it's purple, you know. But observational purity is when something uses side effects on the inside, but it doesn't seem that way to a caller. If I handed you this fact function and it had this implementation, you would have no way actually of knowing that it was this versus fact, good old fact, homeboy fact, the original fact that we defined on the first day of class, right, or the second day. And that means it's observationally pure. So we also call such things a benign effect. A benign effect, basically. Like having this ref cell is okay, it's benign, you can't tell. Okay, and at the end of the day, like computers are kind of like observationally pure things in some sense, at least in this class, right? We're all running on bare metal. But the point is that like this is okay to do. For this particular example, there's no reason why you should. But sometimes it's okay to do, all right? As long as it's observationally still computing a pure function. Okay. In 15451, which is an algorithms class, you race against other people by submitting a solution to some algorithms problem, and you can choose whatever language. And naturally, you can imagine I did all of them in SML. Okay. And by the way, I got like number 10 on a leaderboard once. I beat C++, I beat Rust. Like I'm proud of that. But I will not lie to you that like I have done this thing where I allocated a private ref so I could read from standard input faster, because I wanted the speed. So like I will not lie to you, I have done this, but for this particular one, there's no reason to. Okay, no reason. It's a fun class. Cool. Okay, let's move on from observational purity. We're going to talk about aliasing. All right, aliasing is going to be a good friend of ours, where it's actually not, and it's pointer chasing all the way down. But we decided to make our beds, so we have to lie in it. Crazy. It was already there. Okay. And actually, let me see if I did anything else. So one thing to note here is that we haven't dealt with the case where we actually bind a variable to a pre-existing ref. We haven't really done that. But that is what we are going to do right now. Okay. And this will make up aliasing. Okay. We can alias a pointer. We can alias a box. And I want you to be careful about this because I want you to make sure your mental pictures are good enough for this. For the record, this is like easily testable content. Okay. So this is our example. And if I did it correctly, it should exactly match what's on the board. So let's go through it. Okay. Let's start from the beginning. And what I'm going to do is, as always, draw my store. Okay. First line, I say R1 is equal to ref of 0. So one call to ref, one box, right? So I get a box. And we're going to say this one is bound to R1, and it contains what? 0. It contains 0. Okay. Second line, I say that R2 is now equal to R1. What does that mean? Remember, I said that R1 is still bound to a value, right? Ref cells are values, but they're boxes. So we're just saying that R2 is also this box. Not the contents of the box, but the box. Okay. Not quite. And then if I wanted to do the third line, I'm going to say, oh, this is kind of an interesting concept. I've got an int ref. I have a ref that is referencing an int ref itself. I'm referencing a reference cell, okay? Which means that I'm saying the R3 is going to be a, oh, what's this? I have another call to ref, So I get a new ref cell. This one. We're gonna call this R3. But this one is referencing this. So
yes. I think there is.
no, it's that'll get confusing fast. Contains is an imperfect analogy for what this means. But the arrow is what's going to be better to say. Okay. We call this a finger. We call this a finger because it's referencing that. Yeah. No, it's called a pointer. Okay. Anyways, so we have this box referencing this box right here. And that's what we're done with this, right? We're referencing whatever box was R1 bound to at the time, which is this box, right? Okay. And then next I say, ooh, did I mess up? Yeah, I did. I don't want to take this board down. That R4 is R1. I'm sorry. I'm shadowing R1 with ref of 1. Okay. So what do I get? Well, new call to ref, new box again. So new box, and this time I put 1 in it. Okay. And then R1 is bound to it. So I'm going to take away this binding. R2 is still bound to it. That's fine. Doesn't change R2. But now R1 is this guy. And now what happens if I do R2 colon equals 3? Well, I just go to whatever box R2 is holding, and I change what's inside. So I go here, take away the 0, put in a 3. Notably, this indirectly changes, I say indirectly changes R3. It doesn't change R3's value. R3's value is the same. But if I were to do bang, bang into the room on R3, I would get 3. Yeah. Yes. Yes. We're going to see this in a second. We're also going to need recursive types. Do we need recursive types? I don't know. We're going to use recursive types. There's a review lab problem on this also. Okay. Is everybody clear on this example here? Just follow the diagrams, follow the arrows. Okay. Okay. Let's move on. Blah, blah, blah. Nice pictures that I'm not going to have time to show you. Blah, da, 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 da. Yeah, okay. Okay. This kind of stuff is pretty typical, okay? Pointer tracing. I don't really enjoy it, but you know, it makes for a fun classroom exercise. It's easier to understand if you realize 3 calls to ref, 3 brand new ref cells, okay? That's the important thing I want you to realize. And I'm going to go and change this for posterity so somebody jumping in on the recording doesn't crucify me at a later point. Okay. And also note that like we can't change the contents of the box without a call to colon equals. So while we put stuff in the boxes, the only time the contents of the box actually changed was when I did R2 colon equals 3. Okay. And if I wanted, for instance, this pointer to go here, I would say what? What would I say? What expression would I write if I wanted this to go here instead? What do you think? Where I have this set up. Is equal to? Cool. Assigned to. Yeah. R1. Just R1. Ooh. Ooh. Yes. This is a difficult thing to get across. So the contents of the box are changed to what? Well, I want it to reference this box. So I need to give it the box. R1 is the box. If I did this, remember, okay, here's another easy way to remember this, okay? Suppose I did this, right? Well, what's going to happen here is new box per call to ref. So I put in this, where this guy, actually this won't even type check first of all, but like for a second, like, bear with me. If I did ref of R1, right, I get this guy, which is the new box I just made. And then I actually couldn't do this because that would be unsafe. But like you can imagine, yeah. Okay. Yeah. What do you mean by non-local? If your intuition for closure should still apply in that if a closure captures a box, that box can, the contents of the box can change at a later point on you. If I call a function where like that function f contains this box and I can change that box later, that box will still be changed when I go back to that function. Right. Okay. I don't have an example handy for this, but you'll get plenty of practice on this on the homework. Okay, but yeah, good question. Okay, well, all right. Remember, okay, nothing special about boxes. They're just values. Boxes are values. Pointers are pointers are boxes. Let transitivity guide you from there. Okay. But that's the point, all right? We can pass around boxes like values. They are values. Okay. A pointer is just an integer. Okay. So, all right. And now refs within refs. I kind of just wanted to show you that we can have refs that point to other refs. So let's use this list type. And I wanted to call it alpha L list for a linked list, except I realized I used L list in the last lecture for lazy list. So we're going to call it a mute list. But if you look at this type, it should look very familiar to you. It looks very similar to what we had last lecture. I say that an alpha mute list, a polymorphic type mute list, can be either the empty list or its cons where the tail is a reference to another mute list. Okay? It is a reference to another mute list. And you can imagine the sort of zany hijinks we can get into with this sort of thing. But you don't have to imagine, actually, because I will show you. I'm like Charon guiding you to the underworld. Okay, so here's my example for you. I've got this code right here. R is going to be an int mute list ref. So I put it as ref nil. Let's step through this code, okay? So what am I going to say? What am I going to say about this? What's the first thing I'm going to say if you caught on to my patterns this lecture at all? 4. New box. One's called a ref, new box, okay? So what do I get? I erased my store, but this still is a store, okay? I get R is, oh, I see, okay. I get R is going to be ref containing nil, which is a functional value. It just fits inside of this box, yeah? And then I say that L is cons of, oh, oops. I wanted to do this in a different way, actually. Sorry. I'm going to put it here conspicuously, and it contains nil, and this is R. This is R, okay? And then for this one, no box, right? No box. I'm just going to say I now have a value, which is going to look like this. Cons of 1, comma, this box. Okay, and this is just like a value. It doesn't like really exist in the store, so I guess like it would be inaccurate to put store, but this is how you can conceptualize it, right? I'm making a value where this R is a box that contains nil. Cool. And then this whole thing is going to be L. All right. And then what do? I say, let me reassign the contents of R to be L. What am I really saying with that? This is why the box containing thing is imperfect, because I would have to put this inside of this. Like, that's kind of weird, right? So here's what I'm actually going to do. Contains is an imperfect analogy. The box contains a reference to this cons cell, which exists in memory somewhere, okay? But it contains a reference to this cons thing, all right? And if everyone's cool with this, I'm going to show you that actually, I've reproduced this exact example here, okay? And let me write a fun little function for you. So if you believe me that this is the same as that, I'm going to write a function called traverse. It's going to take in an alpha mute list, and then we're going to say, if I get nil, I'm going to raise div. Otherwise, if I traverse on cons of something and then R, what I'm going to do is I'm going to first print I am going somewhere, and then do a sequencing thing. And this is how I prefer to indent these. And then I'm going to traverse on bang of R. If you believe me, this should type check. Okay. And then it's okay. Let me do traverse on L. Yeah. Infinite loop, because I go here. Don't. Oh, you don't want to ask that. This is like there's something like this on your homework. Not like this exactly. But you know, what I'm doing is I'm unpacking this value, and I go to it, and I call traverse on this, and then I unpack this, and I call traverse on this, and then I'm looping forever. All right. I don't mind wasting compute cycles. Okay, people who study machine learning waste infinitely more cycles than I do on this. All right. I could be doing worse. I could be training a neural network that then runs into a typo 5,000 compute hours in and then crashes. Okay, I could be doing that. People do that. What is it? What? Oh, no, I don't care. Doesn't matter. All bets are off when you control G of the program. Yeah, doesn't matter. Okay. Wow, we're actually still pretty good on time. All right. Cool. Is everyone cool with this example? And note that like we can make cooler stuff than this. I wanted to show you the cycle, but we can make a legit linked list. We can make a circular linked list. Like all bets are off right now. One kind of cool thing to note about like SML values, right? And recursive data types in general that we've seen, right? Is I can't really, so far that we've seen in this course, I can't really have this case where I do node, where node is the original tree we saw a long time ago, where I say it's empty 2 and then like itself. Like I just can't do that, right? It's not really possible because how would I make this thing without being able to refer to this? I could dynamically make like a new node and then infinitely loop, but I can't make it the same node. Yeah. No, val recursive only lets you bind to lambdas. Yes. So even then, yeah. And more likely than not, what you're thinking of, you'll get into an infinite loop. It doesn't exactly matter. But the point is just that like SML values, like when we don't deal with this weird reference nonsense, they're very well behaved because they look like this. You can always draw that. Oh, unless you're talking about functions, you can always draw them. You can always be like, hey, this is empty. And oh, this is node, and then it contains 2, and then there's something here. But it can't do this kind of nonsense. You can always draw on the board without cycles. Okay, that's the nice thing about SML values is they're always like some kind of tree. Okay, you can't have an infinitely long value basically, because you can also imagine like if I did this, I'd have to use infinitely much memory to store it. But with refs, like I can use indirection to reuse this memory. Doesn't really matter. I just kind of like felt like commenting. Okay, is everyone cool with this example, which is nicely illustrated as such? Yes, cool. Okay, honestly, I have you for a bit longer, but I'm just going to talk about some cool applications of mutability. If any of you end up working in a language that strongly prefers to be immutable by default, which is pretty much every modern language, by the way. Like when I'm talking to you about refs, like this is present in Rust, it's present in Swift, it's present in JavaScript. Like this is generally how things trend. Like the fact that C doesn't have this is because C is a dinosaur. Okay, I didn't sign up to teach you dinosaurs, but so what I'm trying to justify to you here is that what I'm going to say next is applicable. All right. Mutability is generally a big deal. It's generally not a good thing, but we don't have to avoid it at all costs. There are some real things I use this for in my work, and I just wanted to tell you a few like cool techniques. Okay. But before I say that, actually, I had a note which was on the very first day I gave you this analogy, and this analogy was like an imperative kitchen. Okay, if we were talking about a kitchen, okay, is that all the chefs are sharing the same ingredients in the same dining area. Does anyone remember this analogy? Hey, let's go. Okay. They have the same dining area, and you put down your plate of pasta or your macaroni, and you come back to it, and then someone's put marinara sauce in it, right? Because they can mess with each other. And I hope now you realize that this was a analogy for parallelism and mutability, right? And in a functional kitchen, everyone has their own dining area or their own preparation area and their own ingredients, so no one can mess with each other. Mutability is a really bad thing when you come into parallel programs. As long as we have immutability, sequential or parallel, doesn't matter. In parallel programs, I can't mess with other threads or processes or things. I literally cannot. Immutability means it's impossible. In the sequential case, mutability can be fine. It can be fine. But parallel, no man's land. No man's land. All bets are off. Like if you come to me, okay, and you write me an email years later, and you're like, Brandon, you said mutability was okay. I was running this multi-threaded program and it crashed on me. I will be like, nope, just don't contact me again. You learned nothing. All right. This is all bets are off. I can't help you. All right. God can't help you when you're here. All right. Mutability and parallelism, you're cooked. You're done. All right. So for stuff like this, it's okay, right? But suppose that someone had been running all of these declarations at the same time, right? What does the diagram become? It doesn't become a diagram. It becomes a probability space of diagrams. It becomes all of the permutations of these declarations, possibly, of diagrams. Okay. No one can cognize that in their brain, okay? Exponential state space blow up. So you're done, all right? That's what I wanted to get across to you. And if you take 15 to 10, they will drive this into your brain more. Okay, and I'm going to show you some, but as an aside, that was an aside, I will show you some cool techniques with mutability, okay? All right, and also like, purity is a trap. Remember, we make immutability work for us. All right. One technique I like to use a lot is fresh identifiers. This is maybe more useful in like a programming languages context, but actually I think it's pretty universal. So basically the idea is, suppose I have like nodes in a graph, or people in a database, or variables in a program, or transactions in my bank system. And I want to make sure that each of those has a unique identifier. Why? Because I want to keep track of it, and I want to be able to uniquely reference it and make sure that I know when these transactions are the same. You might think in a functional setting, that's kind of hard to do because like, isn't the point I need to generate like new things? Well, ref cells are a very easy way to do it. So the simple way to do this is I keep a store at 0, and I have a fresh function, which is of type unit to int. And all that happens is every time I call fresh, I increment this store that exists somewhere in the void, and then I give back whatever it's at. So, you know, the first time I call this, I get 1. Next time I get 2, 3, 4. But I guarantee that over a program's lifetime, I always get unique identifiers. Okay. Does everyone see why this works? Yeah, I personally really like this because this is very handy for my line of work. Okay, but like transactions in a system, people in a database, like this is generally applicable. This is a good like disciplined use of mutability. You know, if you're calling .fresh, which takes in a unit and gives back an int, usually it's also clear from the type, like, yeah, there's some mutability going on here. Okay. But another thing that's cool about this is, or not cool about this, is this thing gives me back ints. But all I wanted the ints for was to be able to guarantee they were unique. What if I take that int and I subtract 3 from it? Accidentally. I didn't mean to, but I subtract from it. And now I'm holding an int that's the same as another int in my database. And then I compare them and I'm like, looks good, they're the same, but I missed the part where I did some arithmetic to make this not safe. You get what I'm saying? Like the fact that it's an int means I can mess with this invariant I sort of have, that unique ints should be unique. Okay. Well, what does an invariant sound like? Well, it sounds like a functor to me, or it sounds like a structure. So what I can do instead, this technique is fine, but to make it even safer, that should be signature, sorry. I can make a signature which has an abstract type T, where fresh gives me back a brand new T. And then I also need an equality function that tells me if two T's, two unique identifiers are the same, right? Because otherwise I can't use them. I'm just holding the T's and I can't do anything with them. And if I have the signature, I can make a structure that ascribes to it opaquely where I do the same thing. The code is the same. But now I hide the fact that it's an int, and I can guarantee that if I'm holding an abstract unique identifier, I can never change the identifier. I can only pass it around. And if you make a mistake at that point, that's on you. All right. But note that I need this equality function because otherwise I would not be able to compare two unique identifiers, which is the whole point. Okay. All right. So fresh IDs, that's one mutability technique. Another one's called hooks. And this mostly comes up in the context of like compilation troubles, which, you know, I'm not necessarily sure you're familiar with, but let me paint a picture, which is that like I've got code, right? And this code exists in like different files. And the code has dependencies, right? Like suppose that I have, suppose we're working in SML, right? And I have a file a.sml. And this a.sml file is actually used by another file called b.sml. And this b.sml is used by another function called, or another file called c.sml. So it goes here, right? This is generally like a bird's eye view of how like dependencies in a project work, right? You could imagine the situation. Well, this means that C can use a function that's in A, but it doesn't go the other way. I can't freely use necessarily something from C in all cases. The compiler is going to yell at you. It'll be like, oh, dependency alert. And this is really freaking annoying, by the way. But this happens for like pretty much everything. So I can't go this way. Like this is impossible. But suppose that there's like some logic that lives in C that I really want at the time of A. Okay. Like maybe C is like computing some like hard to do function, or has types, or it has data that I'm not privy to when I'm living here in A. Okay. Could refactor the code, but sometimes that's really hard to do. My point is that this technique will mean that we can freely do this kind of thing via a trick. And there's lots of reasons why this might happen. But what we're going to do is we're going to call it backpatching. Basically, A is going to set up a box. And in the box is going to be none. But at compilation time, before any code really runs, we run all the top level declarations, which means that before a.sml or b.sml or c.sml really runs, I can have some code from here injected in there. So I'm going to turn this. I'm just going to leave it here for a second, but I'm going to turn it into sum of f, so that by the time that A is ready to use it, this thing contains some code from C. And what you'll find is actually this is a perfectly valid thing, right? Because if a.sml is like, hey, I'm giving you this ref called r, c.sml can then later say r : equals to sum of f, right? That makes sense, right? Because remember, C can use stuff from A. Does this make sense to everyone, or is this like too abstract too fast? Okay. But like the point is like if I give you a ref cell, that means I can now exchange data temporally in the other direction, irrespective of dependencies, because I can just put something in the box at a later point. That's pretty much exactly what this is. Okay, a hook is a ref of type T option ref. We'll say I have a function I need, but I don't have it at this point, and this is in a.sml. Say it's of type int to int ref, int to int option ref. I put none in it, so I put none in the box, and then like later on in C, I say, hey, I have this like cool function f, and I know you need it, so I'm going to set the contents of this box to be sum of f, this function f that I have that you need. And then now when A runs, it has access to the box. It has access to the function. We call this like hooks. This is useful if you want to like dynamically change the behavior of a function, but you want like a user to be able to do it. Actually, the SML&J compiler behaves in this way in a certain sense. There are some refs that exist in the SML top level, and you can like change them, and it'll change how the compiler behaves. So this is like the same technique applied. For instance, there's a ref I used when I was debugging the NJ bug, where like you could do debugging, and it was a bool ref. But what I did is at the NJ top level, I kind of just said colon equals true, and then the NJ compiler changed its behavior because now it is reading from the same place. So the dependency goes backwards, kind of in a sense. Okay, my behavior now can be dependent on stuff later. Which is kind of the whole point of mutability, right? Okay, that's hooks. Sorry if that was a little abstract, but I don't know. I think this is a really useful technique, genuinely. And then I have one final example for you. Global settings. Suppose I'm writing some kind of function, some kind of code, some project, and I have some debug flag. Someone needs to, and if you think about it, right, like if you ever use like some kind of command line program, I might say like SML -- debug, and that doesn't actually exist as a thing, unfortunately. But I'm not going to find one. Yeah, I'm not going to find one. But the point is, like, I can usually set some kind of like setting equals to like false, right? And I want that setting to persist over the course of this program's runtime. The whole time that this program's running, I want this setting to be false. Well, suppose that it's actually a different one. Suppose it's verbose. Like, has anyone ever like worked with like a command line program where you set verbose to true and now it like prints out a lot of stuff? In SML, you could conceive of writing this code as such. I have like some function initialize API, and it takes in an explicit parameter is verbose, and I case on it, and then I print it out. That's not so bad, but you have to think about the fact that like now on every call to this function, I have to pass in my is verbose value, right? That's painful. Suppose I had like 20 different settings I could change, then I got to pass all of them into this function. If I pass it functionally, that kind of sucks, okay? Because it's not going to change over the course of the program. So to show you what I could do differently, I could do this. I kill the is verbose. I set up a bool ref called is verbose somewhere, like at the top level, like up here upstream at a.sml, at the very first entry point to my function. And then I just like bang it. I like dereference it and I get whatever's inside. Okay. And now I don't need to pass around is verbose all the time. This makes my code a lot cleaner at really no cost because I don't expect the contents of this ref to change over the course of my program. It gives me extensibility too, because I can change it dynamically now. Mutability, but in moderation. It's helpful. It saves me some code, but like for these cases, it's like very much clear that like what's the worst case that could happen? Like very little, precious little. It's very hard to make a mistake with this. Does everyone understand this example? I don't know. This is something I think about at my job, but like your mileage may vary. But I think this is a genuinely useful technique you could use in any sort of context. Okay. All right. And then something I didn't do earlier. All right. Well, actually, this is lazy programming, so I don't know why I have that open. I'm not answering that one. All right, cool. Nothing. Okay. That's actually the end of the lecture. But yeah, I'll take questions now. Thank you so much. Welcome to Imperative Programming. Your life is ruined.